Imagine for a moment a sponge, but not a normal sponge. Imagine one so incredibly tiny it can soak up individual molecules. A material so perfectly designed it can literally pull fresh, clean water right out of desert air. Now, this isn't science fiction. This is a real Nobel Prize-winning breakthrough in chemistry. And we're about to dive into exactly how it works.
So let's start with the big news. The Royal Swedish Academy of Sciences has awarded the 2025 Nobel Prize in Chemistry for the development of these revolutionary materials. They're known as metal organic frameworks. And I want to be really clear here. This isn't just some small improvement on an old idea. This represents a fundamentally new way to build matter, literally molecule by molecule.
All right, so here's our game plan for this explainer. First, we'll meet the Nobel laureates who made this all happen. Then we're going to get to the heart of what these molecular sponges actually are. After that, we'll look at the individual contributions of the three scientists, explore the incredible real-world problems these materials can solve, and finally, we'll take a look at the future they're opening up for the entire field of chemistry.
So, who are the minds behind this revolution in materials science? Well, this wasn't the work of a single person having a eureka moment. No, this was a massive collaborative effort, one that spanned decades and crossed entire continents. The prize was awarded jointly to three scientists who, together, laid the groundwork for this whole new field.
The laureates are Professor Susumu Kitagawa from Kyoto University in Japan, Professor Richard Robson from the University of Melbourne in Australia, and Professor Omar Yaghi from the University of California, Berkeley in the USA. It was their combined international effort that really turned a brilliant concept into a world-changing reality. So now we know who's behind it, but what exactly did they create? What are these metal organic frameworks, or MOFs, as you'll hear them called? Honestly, the simplest and I think the best way to think about them is as molecular sponges. Okay, so by definition, MOFs are crystalline materials. That just means they have a highly ordered structure, kind of like a microscopic scaffold or a crystal lattice. They're built by linking two things together: metal ions, which act like the joints, and organic molecules, which act as the long struts connecting those joints. When you put them together in this way, you create a structure that is incredibly porous. It's just filled with these perfectly uniform, sponge-like holes. And that precise structure is really the secret sauce. Because they're built molecule by molecule, these frameworks are surprisingly strong, but they're also unbelievably spacious on the inside. You see, those organized holes, those pores, give MOFs their superpower, the ability to selectively trap, store, and filter a huge range of different molecules, very much like how a kitchen sponge soaks up water. Now, a breakthrough this huge rarely happens all at once. It's more like a story with different chapters. So let's take a closer look at the individual roles these three laureates played. Each one of them made a really distinct and absolutely essential contribution that pushed the whole field forward. First up, we have Richard Robson. You could say he laid the conceptual foundation. He was the first to pioneer the idea of creating these big 3D frameworks by linking metal ions with organic molecules. He showed it was even possible. Then Susumu Kitagawa came along and proved their practical value. He demonstrated that some of these MOFs could be flexible and dynamic, that they could actually expand and contract, almost like a pair of lungs, to grab onto gases and then release them. This was the proof that they could actually work for things like gas storage. And finally, there's Omar Yaghi. He really established a systematic way to build them. He created the first truly robust, superporous MOFs, and he developed what's called reticular chemistry, which is basically a set of design principles, a blueprint for building these frameworks with custom-designed properties. Okay, the science is absolutely fascinating, for sure. But why does it really matter? This is the point where we move from the lab into the real world. Because MOFs aren't just a scientific curiosity, they offer some powerful solutions to some of the most urgent challenges our planet is facing right now. And the potential here is just staggering. Let's look at just 4 major applications. Number 1, imagine a device that can pull fresh drinking water directly from the driest desert air. Well, MOFs can do that. Number 2, they can be designed to selectively capture carbon dioxide right at the source, like a power plant, giving us a vital new tool to fight climate change. Number 3, their internal pores can safely store volatile gases like hydrogen or natural gas at much lower, safer pressures. And number 4, they can act as tiny molecular-sized reaction chambers, speeding up the process of creating new medicines and other important chemicals. All of these incredible applications bring us to a pretty profound conclusion.
You see, the development of MOFs isn't just one more achievement on a long list. It really marks the dawn of a new era in how we create materials. You could call it the era of true molecular architecture. In fact, the Nobel Committee captured the significance of this perfectly. They use this wonderful metaphor, saying that the laureates' work is like creating new rooms for chemistry. What they mean is that the internal pores and cavities inside these frameworks are literally new, molecular-scale spaces where chemical reactions can happen in ways that were just never possible before.
This discovery has given scientists an entirely new toolkit to build materials from the bottom up with atomic precision. It has fundamentally changed our relationship with matter itself. And so that leaves us with one really fascinating question. Now that we have the power to build at the molecular level, what new frontiers will be unlocked next?